Okay, it's all processed. Why does it have already, or source guide is still? Wow, wow, wow! That is quick. Yeah. Okay, so what I need to do is I need to select chapters 3 and 4. That's this week's chapters, and then this material so that the Gemini, the Notebook LM has the lecture transcript as well. And let's generate an audio overview of that. I'm just gonna use the vanilla using those three sources. And the thing that I don't know, and this is where I'm regretting that I didn't think of this ahead of time, is that this could take a bit of time. But when it's done, this is what I want to try. I want to just, have an audio podcast based on these three sources playing. And as it does, I'm going to do it in interactive mode. So I'll be able to interrupt and just to kind of, if I feel like it's misrepresenting something, I can, have a conversation, see what that goes. I haven't tried it. That's really why I keep putting this as part of the agenda here. I want to kind of try out what different things are possible with AI, and I could just do it on my own, but why not to accomplish two goals at the same time? There are I have I guess there are people who don't like the idiom to kill two birds with one stone. Um, I'm fine with it, but then I hear people saying, feed two birds with one stone, which I think just sounds silly. So I don't know. I'll just, yeah, that's still generating. So whenever that's done generating, I'll play it here just so that I'm kind of seeing what it looks like for someone who doesn't have the owner's access, and then we'll go from there. In the meantime, is there something I can do? Um, hmm, I guess I could, Oh, I think that source made it here, so um, chat with chat about the sources. Select down to these three and ask, "Hi, can you give me 5 main points from this week's material? I selected three sources that match to this week's material," and it'll give you some 5 point summary. And let me tell you if how that feels to me. um, yeah, work energy theorem, uh, and yeah, kinetic energy is pretty important. Potential energy and conservation of conservative forces, where yeah, only when only conservative forces to work, then yeah, mechanical energies constant. Yeah, linear momentum and Newton's laws. Yeah, impulse and chain. Did they talk? Yeah, yeah, general form of Newton's second law. Yeah, that's good. Uh, Social momentum principle. Yeah, I think that's a good summary. Let's see. Did they miss anything? Oh wait, did it talk about Newton's cradle? Maybe, or cradle. Ah, didn't talk about Newton's cradle. So let me say. I thought I saw a lecture sec- segment on Newton's cradle. Can you tell me more about that? I mean, it's a kind of the thing that's illustrated in Newton's cradle is captured in that overview of conservation of energy and momentum. I think I use Newton's cradle in two different places. There's kind of intro as part of lecture 8, and I bring it back later. Yeah, it's capturing both, right? So there's a collisionless simulation. Yeah, yeah, that's good. Yeah, yeah. Yeah, yeah, yeah. No. Yeah. Is it still generating? Yeah. Okay, I think it might have finished generating. Let me refresh here. And if it pops up, then I will. Yeah, okay. So this is what I'm gonna do. I'm gonna play this podcast. I'll do it in interactive mode. And I need to make sure that I share my audio so that people hear it on Zoom. And now this is the part. Let me try doing it this way, and if it works horribly, then I'll do something different. So for my backup recording, I have that it has ability to capture desktop audio, but I usually have it turned down because when I use this, I usually don't want the recording there to capture the like the computer sounds. Um, but let me have the desktop audio on here so that what it's playing through my computer speaker that you will hear through Zoom, that it's captured in this recording in a local way. I'll see how that looks. Sometimes that audio getting captured both through here and through my microphone here can be distracting, but we'll give it a try. I don't, if it looks horrible, then I don't have to use any of it. Let me make sure I share my audio here so that I'm doing it here. Make sure that I'm sharing sound here so that you can hear what I hear. So I'm gonna just play and then see how that goes. So interactive mode. And can I make this? Okay, that's gonna be as big as it can be. All right, so I'll see. Play, and does it have size setting? Yeah, I'll just play it, and I'll see later if when I join, if I need to watch out for the microphone permission.
So I have this entirely hypothetical job offer for you.
Okay, I'm listening.
I want to hire you to hold a heavy rock, let's say a 50-pound boulder.
Sounds awful already.
Right, and I want you to hold it at shoulder height, perfectly still, for 8 hours straight.
My shoulders are literally burning just thinking about that.
But here's the catch. At the end of the day, when you come to collect your paycheck, I'm going to tell you that according to the strict laws of physics, you didn't actually do any work.
Wow.
So I'm not paying you.
And this is exactly why physicists don't get invited to many dinner parties or labor disputes.
It sounds like a complete scam, doesn't it? But that is our mission for today's deep dive.
It's a fun one.
We're looking at a great source today. It's Chapter 3 from the Introduction to Physics textbook by Park via OpenStax.
Great resource.
And we are going to try and fix this massive communication breakdown between everyday English and actual physics.
It is a huge gap, honestly, because we use words like energy, power, and work every single day.
Yeah, to mean effort or feelings.
Exactly, or just electricity. But to a physicist, these are very rigid mathematical concepts.
So if you're listening right now and you mix these up, you don't just, fail a test. You fundamentally misunderstand how the universe operates.
That's entirely true.
So I want to get to the bottom of this rock-holding scam. But I also want to understand, for instance, why a roller coaster doesn't go faster just because you load it up with heavy people.
A classic puzzle.
And why my car's stopping distance doesn't just double when I double my speed.
All of those puzzles stem from the exact same root. The true definitions of work and energy.
Are they coming from?
Okay, so let's go back to my boulder. I'm standing there, I'm sweating, my muscles are visibly trembling. I feel like I am working harder than I've ever worked in my
I
life.
feel like you
Naturally.
might be making stuff.
Why does this textbook say I am doing zero work?
Well, it comes down to the scientific definition of work. For work to happen, you need two ingredients, and you really need either one.
Okay.
First, you need a force. You have to push or pull on something.
Check. I am actively pushing this rock up against gravity.
Right. But second, and this is where you lose your paycheck, there must be displacement.
Meaning,
The object has to actually move.
and since I am holding it perfectly still,
The displacement is zero.
okay,
The equation is W equals F times D, force times displacement. If that D is zero, the whole thing just collapses to zero.
it doesn't matter how hard I'm pushing.
Doesn't matter at all. If the rock doesn't go anywhere, you haven't done work on the rock.
But I'm tired. My body depleted energy. Where did it go?
See, that's a biological question, not a physics question about the rock.
Oh, I see.
Your muscles are doing microscopic work. The fibers are contracting, relaxing, twitching constantly just to fight gravity.
So I am doing work inside my body.
Yes, you're burning calories, you're generating heat.
I don't know why it's focusing so much on this early part. So let me try doing this. I'm gonna just let it play for, I don't know, another 5 minutes or so. And then if it's still on this about, how why holding a heavy rock is zero work, then I'll try to ask it about later part of chapter 3 and also chapter 4. And let's see how adaptive this interactive audio overview is. So let me just let it continue playing for about 5 minutes. I'm gonna just set a timer, and then we'll see.
But externally, to the universe looking at that boulder, nothing happened.
That is genuinely maddening.
The rock has the exact same energy at 5 p.m. as it did at 9 a.m.
Okay, fine. So I need to move it. Let's say I start walking. I'm carrying this 50-pound briefcase or rock, whatever,
that is
and I
textbook.
walk a mile down the road.
Okay.
I am moving now. Displacement check. Force check. Do I get paid now?
You're gonna hate me.
Oh, no. Don't tell me.
You still aren't doing any work on the rock.
You have got to be kidding me. I moved it a mile.
You did, but think about the direction of your effort to keep that rock off the ground. Which way are you pushing?
I'm lifting it up vertically.
Right. And which way are you walking?
Forward. Horizontally.
That is the problem. In physics, the force only counts as work if it's pushing in the exact same direction as the movement.
Wait, so because they're perpendicular?
Exactly. You're pushing up, moving sideways. They are at a 90-degree angle. They don't talk to each other.
So the vertical lift doesn't help the horizontal motion at all.
Nope. So technically, the work done by your lifting force is zero.
So the only way I do work is if I actually lift the rock higher.
Boom. That's it. If you lift it from your waist to your head, force is up, motion is up. That is positive work.
And what if I lower it?
If you lower it, your force is still up because you're holding it from falling, but the motion is down.
So they're opposite.
Right. That's called negative work. But lifting it up, that's positive work. You've successfully transferred energy from your body into the rock.
Okay, I think I'm starting to get it. Work is basically a transfer of energy.
Yes.
If I'm not changing the rock state, like lifting it higher or speeding it up, I am not doing work.
That is a brilliant way to put it. Work is the bridge. It's the action of moving energy from one budget to another.
And speaking of amounts of energy, the text brings up the joule.
Ah, the standard unit of energy.
Yeah, and it really surprised me how small a joule actually is.
It's tiny.
The example they gave was lifting a small 100-gram apple about 1 meter in the air. That one motion is roughly 1 joule of work.
Which really puts things in perspective when you see a diet label saying you just ate something with thousands of joules of energy.
Right. Okay, so let's talk about those buckets you mentioned. Once I've done the work, say I push a heavy package on a conveyor belt and get it moving, where does that energy live now?
Now we are in the realm of kinetic energy, the energy of motion.
Now, intuition tells me this should be simple. If you have a car moving at 10 miles an hour and another moving at 20 miles an hour, the fast one just has double the energy, right?
You would definitely think so. It feels like it should be linear.
Right.
But nature is a bit more dramatic than that. The formula for kinetic energy is 1/2 times the mass times the velocity squared.
Squared. So it's not times 2, it's times itself.
Yes. And this is honestly one of the most important concepts for anyone listening who ever drives a car.
Because of the speed.
Exactly. If you double your speed from 20 to 40, you don't double the energy. 2 squared is 4. You actually have 4 times the kinetic energy.
That sounds terrifying when you put it in the context of a car crash.
It is. It's exactly why highway accidents are so cataclysmic compared to a fender bender in a parking lot.
Because the energy scales up so fast.
Right. If you go from 30 miles an hour to 90 miles an hour, tripling your speed, you don't have 3 times the danger. 3 squared is 9. You have 9 times the destructive energy to dissipate if you hit a wall.
And this connects directly to stopping distance too, doesn't it? I remember the text talking about the work energy theorem.
Yes, which is really just a fancy way of saying the net work you do equals the change in kinetic energy.
So stopping a car requires work.
Exactly. When you hit the brakes, your brake pads are doing negative work. They are forcibly stripping kinetic energy out of the car, turning it into heat.
Negative work. It sounds like a corporate buzzword for wasting time.
I know, but in physics, it just means the force is fighting the motion, the car is moving forward, the friction is pushing backward.
And that friction has to eat up all that energy.
Precisely. So if you're going 3 times as fast and you have 9 times the energy, your brakes need 9 times the distance to eat it all up.
9 times the distance. So the difference between stopping at 50 and 70 isn't just a little bit further.
It is vastly for it is the literal difference between a close call and a tragedy. And it's all because that little v in the equation has a 2 hovering right above it.
Okay, let's park the car for a second. We've talked about the energy of motion. But what about energy that's just sitting there? The textbook spends a lot of time on potential energy.
This goes right back to your rock. Remember when you finally did some work and lifted it over your head?
I do. My back certainly remembers.
So you transferred energy into the rock by doing work. But the rock isn't moving. It has no kinetic energy. So where is the energy?
It's stored.
Yes. It is now gravitational potential energy. It successfully fought gravity, and now gravity is just waiting for its chance to pay you back.
So gravity acts almost like a battery.
That's a perfect analogy. By lifting the mass, you charge the battery. The higher you lift it, the more charge it holds.
And the formula for that is really simple too, right? Mass times gravity times height.
Very simple.
I love the example the text used for this, a cuckoo clock.
Oh, yes.
You pull the chain to lift the heavy...
It's been 5 minutes, and I guess it has moved on a little bit. It's talking about potential energy, but since we only have, 15 minutes left, let me just interrupt and ask for kind of coverage of both the later part of chapter 3 and chapter 4, impulse and momentum, which they might not be getting to it at all. And I was just looking to see, following some of the material in the source, and so mathematical expressions you can't quite see here, but I guess I can ask. I can ask something like, so I was listening to the audio overview covering chapter 3, and the hosts were, let me not put scare code, hosts were talking about kinetic energy, and in the portion of chapter 3 source covering kinetic energy, I couldn't see the mathematical expression. Can you give me a quick report that includes the math expressions? And it'll do that. So let me resume playing, and I'll interrupt and ask for the rest of the content that I'm afraid that they might not be getting to. Okay.
The iron pinecone weights. You are... Whoa, did someone just break the fourth wall? Let's hear it.
Hi, I'm really enjoying this conversation about how I'm not going to get paid carrying rocks, but I really need to cover chapters 3 and 4 this week, and I think there are some lectures that I kind of watched through, but I don't remember all of it. So I was wondering if you could help me quickly review the rest of the chapter 3 and the key points from chapter 4, and whatever was covered in the lecture that's part of this week 5, that I watched through, but I can't quite remember all the details. Thank you.
Absolutely, we can totally shift gears for a few minutes.
We love the flexibility. We can definitely hit the key points you need.
Okay, so you're asking about the rest of chapter 3, which is the work and energy chapter.
And you mentioned chapter 4, which is the impulse and momentum section. That is the next unit.
That's right, and the lecture you watched was about that transition.
So we can quickly wrap up chapter 3, touch on the big ideas of chapter 4, and connect them.
Let's quickly finish chapter 3 first, since we were just talking about the cuckoo clock.
You pull the chain to lift the heavy iron pinecone weights.
You are doing work, storing potential energy.
And then as those weights slowly fall, they run the clock's gears. It's a beautiful visible transfer.
And a core concept in chapter 3, which is tricky, is path independence.
That's right. It means that whether you lift that rock straight up a ladder
or carried up a long spiral staircase,
the work done against gravity is the same as long as the starting and ending heights are identical.
Because the universe only cares about your altitude, not your itinerary.
You trade force for distance on the stairs, nature balances the books.
And this idea of balancing the books leads to the main rule: conservation of mechanical energy.
That's the holy grail of the chapter. Energy just swaps between motion and height.
The classic example is the roller coaster. We have maximum potential energy at the top.
And as it drops, that potential turns completely into kinetic energy.
Which brings up the weirdest idea, the magic of mass.
The fact that a full car and an empty car drop at the exact same speed,
My brain still rebels against it. Heavy cart, bigger force, so faster speed, right?
that's where you forget inertia. Mass determines how hard gravity pulls.
But mass also determines how hard it is to get it moving.
Exactly. The extra pull is perfectly canceled by the extra stubbornness of the mass.
So they cross out mathematically. The speed only depends on the height.
It's mathematically poetic. Galileo was right.
Now, a very practical application we touched on for Chapter 3 is the physics of impact.
This is work-energy theorem again, where the network must equal the energy change.
If you jump off a wall, the ground must do work on you to stop you.
And you choose how you stop by choosing the stopping distance.
Knees locked, stiff-legged, tiny D, enormous force, bone-shattering.
Bend your knees, you increase the shive by 100 times, and the force is manageable.
This is also why airbags work. They increase the stopping distance.
We also talked about the biological version of this, kangaroos.
Oh yes, the physics geniuses.
They use elastic potential energy, scoring impact energy in their tendons.
Like biological pogo sticks recycling their kinetic energy for the next hop.
Which is much more efficient than humans, who lose most impact energy as heat.
And the final part of Chapter 3 is power.
Ah, the one that everyone confuses with energy.
Work is the task. Power is the schedule. It is work divided by time.
Sprinting up the stairs requires the same work as walking up.
But you output way more power because you did it in less time.
You're just burning the energy faster, which generates more heat. That's why we sweat.
So that wraps up the key concepts of work and energy in Chapter 3.
Now let's pivot to Chapter 4, impulse and momentum.
This chapter continues the theme of conserved quantities.
Momentum, often defined by the symbol P, is simply mass times velocity.
Unlike kinetic energy, momentum is linear, it's not squared.
And the key principle is the conservation of momentum.
In a collision, the total momentum of the system before must equal the total momentum after.
The textbook mentions the PhET simulation collision lab, which is great for this.
That's right, the one where you can change the masses and velocities of the balls.
Momentum is critical because it explains collisions when energy might be lost.
Because in many collisions, like a car crash, kinetic energy is absolutely lost to heat and deformation.
But momentum is always conserved, even in totally inelastic collisions.
The lecture you watched also touched on impulse.
Impulse is basically the change in momentum.
It's defined as force multiplied by the time that force acts.
So impulse is just another way to transfer momentum.
Remember how we talked about airbags and bending your knees to spread the force over distance?
Impulse does the same thing, but it spreads the force over time.
If you extend the time of impact, the t, in the impulse equation, you decrease the average force.
Like catching a raw egg, you pull your hand back to increase the time, reducing the impact force.
That is the ultimate connection between the two chapters.
Chapter 3 uses work to manage force over distance. Chapter 4 uses impulse to manage force over time.
Both are about avoiding catastrophic forces by spreading the impact out.
There are massive shortcuts through complex dynamics problems, like the tranquilizer gun.
Ah yes, that example shows the power of the energy method.
Imagine calculating the dart speed with forces, which constantly change due to the spring.
That would be a calculus nightmare, as the force drops as the spring uncoils.
But with energy, you just say elastic potential energy equals kinetic energy.
You don't even care about the messy middle part.
Exactly. You just compare the bank balance at the start and the end.
That's right, the energy method is a massive shortcut through the math.
Does that hit the main points you were looking for, the rest of Chapter 3 and the key ideas of Chapter 4?
We have one final piece of a puzzle left to cover, which is power.
We briefly mentioned it, but it's important to differentiate it from work and energy. Yep, go on.
Yeah, I really appreciate the summaries of the chapters 3 and 4. They're really helpful. Can you tell me, I think it's the lectures, I forget the numbers. It's a lecture for week 5. I think there are 3 lectures. Can you tell me a little bit about key ideas covered in those lectures?
We can absolutely do that. That is an excellent request.
Those lectures for week 5 and the numbering can get tricky, really start diving into dynamics.
You're referring to the beginning of the Forces of Newton's Laws content, which is Chapter 2?
Yes, the week 5 lectures kick off the study of the causes of motion, which is dynamics.
Specifically, the key ideas covered were Newton's 3 laws of motion and the fundamental concepts of force and mass.
Right, and since that material was borrowed from an older class, it was mostly conceptual, which is great.
The lectures emphasize that force is simply a push or a pull.
And they introduce Newton's second.
Oh yeah, let's hear it.
Sorry, I don't think it's those. I looked at the sources, so it looks like it's lecture 8 that's starting this week, and it's, I think, lectures 8, 9, and 10. I don't know if that's part of the material that you have.
That is fantastic. Thank you for correcting us on the lecture numbers.
We appreciate the clarification. Lecture numbering can be all over the place.
Okay, so you are spot on. It is Lecture 8 that kicks off the material we are currently in.
Lectures 8, 9, and 10 cover the entire mechanical concept section, which is Unit 2.
Specifically, Lecture 8 is Energy, Work, and Kinetic Energy. We've essentially been talking about the
Energy
content
1.
of that lecture.
That's the one that introduces the concept of energy and dives into the work-kinetic energy theorem.
It has the Newton's Cradle demo, which is a classic.
And that demo really drives home the conservation idea and the transfer of momentum, even though it's technically in the energy lecture.
And Lecture 9 is Energy 2, Potential Energy, and Conservation of Mechanical Energy.
Which is where we talked about the cuckoo clock and the roller coaster.
That's where you learn about the different types of forces, like conservative versus non-conservative forces.
Conservative forces, like gravity, are the ones that let you store potential energy.
The ones that follow the rule of path independence, which we touched on earlier.
And then Lecture 10 is momentum and collisions, energy and momentum together.
That's your Chapter 4 material, bringing in momentum, impulse, and collision analysis.
They often use the algodo simulation in that one to demonstrate inelastic collisions.
And that lecture ends the week with a review of the Chapter 4 homework questions.
So those 3 lectures are essentially everything we've covered today: work, energy, conservation, momentum, and impulse.
The only part we really have left that we skimmed is the final piece of Chapter 3, which is power.
Yes, we briefly mentioned it, but it's important to differentiate.
So I think in the interactive mode, when you interrupt it and you will address, and it comes back to finish up what you interrupted. I mean, it's interesting. So let it finish playing. I think it only has maybe a couple minutes of material left that's like in the what it would have been in the audio overview before I started interacting. So let me just let it finish playing.
It from work and energy.
We say power is a schedule, right? Work is the task.
The formula is power equals work divided by time, and the unit is the watt.
1 watt is 1 joule per second.
We talked about sprinting versus walking up the stairs.
The work done is identical.
But the power output is much higher when sprinting because you do it quickly.
You had to burn the energy faster.
And this is where the term horsepower comes in, which is a great historical link.
Yes, James Watt needed a way to sell his steam engines way back when.
So he compared them to the standard industrial machine, a horse.
1 horsepower is roughly 746 watts of output.
We can output that power, but only for a very brief burst of time.
Because we are limited by our radiator, which manages the heat.
Our body generates a massive amount of waste heat when we convert fuel to work.
You would literally cook yourself from the inside out if you tried to sustain that high power for too long.
A horse has a larger capacity to deal with that heat and sustain the power output.
This idea of waste heat leads us to the big picture I wanted to end on.
Efficiency is the tax of the universe.
We talked about energy changing forms like chemical energy in coal to electrical energy.
And at every single step, you lose some of that useful energy to low-grade heat.
Not that the energy disappears, because the conservation we discussed in Lecture 9 still holds.
Exactly. It just turns into a form you can't harness for useful work anymore.
The text points out that a typical power plant is only about 35 to 40% efficient.
Meaning for every 100 units of fuel, 60 to 65 are just warming the air around the plant.
And even our own bodies are only about 20 to 25% efficient when we run.
The second law of thermodynamics is always creeping in. Chaos increases.
Useful, highly concentrated energy always wants to spread out and become useless heat.
This really connects back to the grand ideas of E equals mc squared, as the source mentions.
Mass is energy. Energy is everything.
But the universe constantly degrades that useful energy into unrecoverable heat.
That is the fundamental struggle of civilization, trying to harness that energy.
We are essentially engines trying to extract organized work from a universe that imposes this heat tax.
So next time you pay your electricity bill, remember you're only paying for that efficient 35%.
Exactly. Or, next time you're holding a heavy box and someone tells you you're doing no work.
You have my full permission as a host to drop it on their foot.
See how much kinetic energy they think it lasts then.
It certainly does. Keep looking for the physics out there.
We absolutely love it when you join in with your questions and corrections.
We'll see you all in the next deep dive.
Yeah, I don't know how many times I'll be doing this. I thought I'd try it. Let me know how, for those of you watching, how it feels. If people want me to do it again, I'll do it again. I might try to think of something else to try at the next week's virtual class session. Maybe. I probably should label this. Let me label this as... oops.
So I have this
I thought I could rename it.
entirely hypothetical.
Oh, wait, I'm in the wrong account. That's why. Let me rename it here. Renamed, and I'll just add the chapter 3. So people have it. Yeah, so, and I think that's our time. Thanks so much to those of you joining by. I recorded the video, and I'll see you next week. Bye.